Hi, good evening. We'll start in a while. We'll wait for another couple of minutes and then we'll start. Okay, good evening, everyone. I think we can start now. I hope my audio is
Yes.
fine. My name is Umair Hussain. I'm a PhD scholar in Department of Mechanical Engineering at IIT Madras, and I am taking your doubt session for the course Finite Element Method, Variational Methods to Computer Programming. And so far we had discussed till week 7 content for this course. So I had to miss a couple of sessions earlier in the beginning of this month. So to make up, we are here today. So Today we'll be discussing the content of week 8, and by this we'll cover up whatever we had left earlier. So this course, just quickly revisiting what we had done earlier in this course. So we had started with the variation principles in mechanics, variation methods, minimization problem that is used to get the governing equation for any physical problem. And from that we framed a foundation for FEM, and then we next move to the basic steps in finite element method. So after that we started with the 1D FEM. In 1D FEM, we discuss certain standard problems in mechanics, especially the bar problem, the truss problem, the beam problem, and finally we'll conclude the discussion with a frame element problem that combined all the concepts that we had discussed before. So so this concludes the discussion on 1D FEM. So next we had to move on to 2D FEM. So before that, we spent a week on discussing basic calculus that could be used in deriving especially the weak form for 2D FEM. Then after that, last week we began the discussion on 2D FEM and with the scalar field problems. So this week also we will continue the discussion. So first of all, I start again with the question that what do you mean by the scalar field problems in 2D FEM? Anyone any has any idea what are field problems in 2D FEM?
Oh, I think in these type of problems, as an input, we have some scalar. We have some scalar quantities in terms of two dimensional, because here the word is 2D FEM scalar field problem. For
Yes.
example, heat flux we know, or temperature at any particular wall of the uh, any part, or anything that is given to us. So I think that's why the name is a scalar field problem.
Yes, right. So basically, what we are solving for, the primary variable that we are solving here for is only is a scalar variable. So there's only uh, it's a scalar primary variable. Like you said, if we have a heat conduction or heat problem specifically, so we are only solving for one field, that is temperature.
Umair, one doubt I have regarding here the this word is scalar.
Yeah.
For example, suppose the third person is asking about stress and strain, and he want to idealize those two quantities by mapping these two quantities in a 2D frame. So at that particular case, can we say the stress and strain both as the vector quantities instead of tensor also, or we have to say in that particular case also we have to say those two quantities as tensor?
Uh, Stress and strain, particularly our tensor quantities, we can represent the tensor quantities as a vector. There's something called Voigt notation.
Mm-hmm.
But when we're solving the problem for stress and strain, uh,
Mm-hmm.
in the conventional FEM problem, those are not our primary variables.
Yes.
The primary variable there is the deformation field or the
Yes.
displacement field. So
Okay.
that itself is a vector quantity.
Mm-hmm. Yes. Okay.
Yeah. In that case, but talking about stress and strain especially,
Mm-hmm.
there are ways where we represent them as vector to
Okay.
simplify our calculations particularly.
Okay. Okay. Okay.
you can dig up something about void notation.
Okay.
Okay. So yeah, opposite to this, for scale, for vector field problems, there are more than primary variable here. So it's a set of primary variables for vector field problems.
Okay.
Classic example is our elasticity equation. We have displacement in x, y, or even z.
Okay.
So last time we started with 2D FEM. We started with a discussion on the weak formulation, then the discretization, uh, and then we did discuss the triangular elements theorem.
Mm-hmm.
So how to discretize a 2D domain using triangular elements, and what kind of approximation functions can be used there. So I think last time we only discussed linear approximation functions. So for so okay, we'll discuss that later. So next thing was to map the domain of any random element to a standard triangular element.
Yeah.
So here we had some standard approximation functions x. So we discussed the concept of the Jacobian there, and unlike in 1D case where we just had uh, this as only this term as a Jacobian. Now since it's 2D, we have to take evaluate four different terms. So it's a matrix basically this time. So we did discuss this last time. So next part. So basically, what we had to transform is this integral, which here this is a vector, and this of two is a vector, and we had to transform this into so this can be done using the Jacobian. Then we'll also have area term here, VHC. So we had a conversion formula here. It was derived in the class in the lecture.
Yeah.
So anyway, at the end, this would be our this would be our final transformation of the integral. So this is something similar to what we did in 1D. Now since we are dealing with 2D, we'll have complicated vector and matrix multiplication.
Okay.
So next thing is the numerical integration part. So we did discuss numerical integration in 1D FEM. There we discussed something known as the Gauss quadrature formula. Again, this same thing we'll do, Gauss quadrature rule. So in I think in every FEM solver, I think more than 90% of FEM solver only Gauss quadrature rule is used.
Yes.
And so the formula again for like for 1D, it's a 1D element. So suppose we are taking considering only one point. So in 2D domain, we'll have this point. So now we'll have some this point. Now we'll have like this, if we are taking 1 point, we have 1.2t domain like this. Now if we are considering 2 points for 2D domain, we'll have 4 points. Sorry, these are not actually nodes. They are nothing. These are not receivable nodes. So if I make every input element like this, so now we'll have four quadrature points here, and likewise if we'll go to corresponding to three Gauss points in 1D, we'll have 9 for 2D. So again the formula goes the same. We'll have I equals C divided by the value of the function at each coordinate of the Gauss point and multiplied by the respective weight functions. So for example, I've written for 1 point and 2 point. So this corresponds to only 1 point, and the weight is 4, and this means four different points, and weight is 1 for each. Okay, so yeah, this is pretty straightforward Gauss numerical integration we'll follow. Now, until now we only discussed linear approximation functions for triangular elements, which were these. If I think the last time also discussed, if we'll have some random shape of the triangle, some random triangle, we can derive the approximation function for that also, linear
Yeah.
approximation function. So next, for if we'll have if we want higher order approximation function, there are methods to derive that also. If I remember correctly, now this one we can have. I'll send you the page line. Okay, so then in order to derive the approximation function for each node, we just need to know where that function would be zero. So an example I discussed last time. So like the approximation function for this node, it will be zero along this line and along this line. So it can be approximated by some constant times, the equation of line length. So that is how we can derive for any node, the approximation function for any node.
Yeah.
So next we discuss the quadrilateral elements. So like we have a standard triangular element 0, 0, 0. So for quadrilateral element we have this standard function which ranges from zeta equals to -1 to +1 and eta equals to -1 to +1. So this is something what similar to what we discussed in 1D, right? In 1D also we had only one xi variable, and it ranged from xi equals to -1 to +1. And in 2D we'll have eta also ranging from -1 to +1. So now the approximation function would have one more term in it. So earlier we had for triangular elements we had only linear approximations. We had
Mhm.
only three nodes. We have a1 a0 plus a1 plus a2 a2. And so this was a way of a complete representation of a linear polynomial. But for For quadrilateral element, we'll have one more term. So since we have one more node, so this type of approximation will be called bilinear shape function or bilinear approximation. So it is linear in both xi and eta separately. So we can say that this is a second order term here, but it's bilinear. So these are the approximation function for this type of standard element. And again, if you want to develop the mapping, we can using this function. Same thing that we had discussed in 1D again also. One thing that uh, we should be careful about is that the Jacobian of this transformation, the determinant of the Jacobian should always be positive because it represents the ratio of two areas basically. Since what we derived earlier, yeah. Jacobian here is actually a ratio, so
Yeah.
it's supposed to be positive. So that is why in FEM certain type of elements are not allowed. Okay, so this was all theory till here. Next, we discuss how to develop the algorithm for the 2D FEM problem. So that's what this is one thing that I really liked about this course. So in practical, we actually have to develop. We can't solve a real life problem by pen and paper, right? So we need to develop a code for that. This is what I really liked about it. They've specifically given the algorithm of how to go about writing your own code. This is really helpful. So firstly, in any FEM program, we need to give the mesh information. That is the domain and all the known coordinate data. So mesh information basically involves three main things. First two are main regarding mesh thing. First is the connective node coordinates and connectivity. Node coordinates will tell you the coordinates of each node present in the mesh, and connectivity tell you the how each node has been used to meet each element. And third thing is boundary information. So boundary information will give will give us an idea of the boundary conditions given to the problem. So we'll discuss a little more about it later. So next is we should know the Gauss points and the weight data. We'll have some input for that. Then we'll have the shape function that we will use. So it depends on the type of element we are using. We'll have the corresponding shape function for that, and also the derivative. And these should be calculated at the quadrature function, because at the end of the day, we're going to solve the integrals, for which we are going to use the Gauss quadrature rule. And when we are applying the Gauss quadrature rule, we'll have to calculate the values and the derivative of the shape functions at the quadrature rule. So we should have some function which will give us that. Then in the processing part, our main processing part comes when we have this loop over each element. So we go over each element, and for each element we develop the element stiffness matrix, element force vector, and we calculate the Neumann boundary term, and simultaneously we add the respective element stiffness matrix and force vector to the respective position in the global matrix and vector. So at the end of the step, we are ready with our stiffness matrix and force vector. Then final, then the next task is to apply the Dirichlet boundary condition. So this is the same way that we did it one day again. We identify the nodes which are at the boundary where Dirichlet boundary condition has been applied, and we reduce the stiffness matrix and force vector, and we modify the force vector exactly as we did in one. Then we after we modify our stiffness matrix and force vector with the boundary condition, we solve the equations, the matrix and vector, to get our solution value for each node. Then we plot the result to be properly visualized. So this is the gist of the basic algorithm to solve any FEM problem. So yeah, this boundary information part, this is something new for me also. So it's a nice way to organize our boundary conditions. So I took a note of it. So basically, it is a matrix which will have the number of rows equals to number of elements. So we'll for each element we'll give some data whether it's present on a boundary or not. Whether it, so it which vertex of it is present on which boundary, if there's any boundary condition present there, what type of boundary condition present. So we'll have number of rows equal to number of elements, and the number of columns would be equal to number of edges. So I hope it was clear now. Okay, then suppose we are going for this element. So if any of the edge is internal, suppose these two edges are internal, that means they are not on boundary. That means there is no boundary condition applied. We just fill them with zero.
Okay.
And it's just a convention. So if there's if the if at any edge there's a restricted boundary condition applied, we assign it a negative number. And if there's a normal boundary condition applied, we assign it a positive number. This is just a convention of numbering, so that we'll know if it's a restricted boundary condition or not boundary condition. Yeah, so this is about specifying the boundary information. So yeah, I think this is it. Then we discussed a little about the details of the program that we'll try out later. Yeah, so this was the main gist of the content of week 8. If there's any doubt, we can discuss it.
No, I have just one two doubts regarding the questions asked in the assignment of week 8, where the shape functions on 2 3 nodes were not matching when I have solved from my side. So just those 2 3 questions I have as a doubt. Yeah.
Please go ahead.
Uh, okay. So can I ask now, or further you will take those?
You can ask now. Wait,
Okay.
if you want, I'll open the assignment also.
Okay.
I have it on my system. Yeah.
Okay.
Yeah, you can go ahead.
Okay. Oh, actually, Umer, those were not related to the shape functions. Actually, these were related to the stiffness values at different nodes of the element 2, that is triangular element. For example, question number 17, if we are taking K11 of the element 2, can you solve this question from your side? K11 at element 2.
Okay, okay,
Yes. Actually, here what they did and what I was expecting, my answer was differed from the given answer by the factor of 2. So I think this was due to some arbitrariness of that shape functions. Maybe I am thinking so, but what is exactly from your side? Please tell me.
okay, okay. If we'll get time, I'll try to discuss this.
Okay, okay. Because these are, I think, 4 to 5 questions successively. These were asked.
Okay.
Yeah.
So here it's a heat conduction problem.
Hmm.
and we're giving this domain a quadrilateral and a triangle.
Yes.
Okay, so what do you say if we discuss the problems first and then we'll see if we'll have time? Because I don't have the code ready for it. I'll try to do it with manually.
Okay.
If it requires the code, then can we discuss in the coming Tuesday, day after tomorrow?
Yeah, yeah, but I think in determination of this stiffness value, you require only two, three, four values of shape function only, and that manually you can try. But yeah, if it is suitable, we can discuss in the upcoming week
Sure,
also.
sure. Yeah, yeah, I'll try if it's possible. I'll try.
Okay,
Okay, then we'll move on, or we'll try this first. If we
okay,
have a doubt, we should try to get over it as soon as possible. So I'll just leave it. So we have to evaluate for element two, right?
yes,
So K1 of L, do that. And since okay, so we'll have this triangular element here.
yeah,
Okay, K equal to 2. Uh, so just to confirm with you, did you see that for this triangular element, the conductivity is 2?
yeah.
Okay, watt per degree Celsius. Because for element 1, it's 1. I thought maybe.
Oh, I think that is the factor I forgot to multiply. Yeah, yeah, yeah.
Okay, that's why
Okay.
this struck me.
Yeah, I think now there is no need to solve for further because there
Yeah,
was a
I got it. Sometimes, sometimes we can
yeah,
just see the source of error.
yeah,
Okay, so we'll not proceed with this further.
yes, yes, I got it.
Maybe in the next class, I'll try to get the code and we'll try to do it using the code also. We'll check
Okay.
it. Okay, then we'll move on.
Yeah,
Okay, so we have a three noded triangular element whose coordinates are 0, 0, 3, 0, 1.5, 1.5. Okay, so Find the value of all three interpolation functions at each node, then at the center of the triangle. So at each node, I think we know the answer for this. Psi 1 at node 1 will be 1, at node 2 will be 0, and at node 3 will be 0.
Yeah.
Likewise, so we'll verify that too, but we need to find the center of the triangle. Okay, so how do we go about this? So here the solution should be a naught plus a1 plus 2y, and it should also be equal to u1 psi 1 plus u2 psi 2 u3. So we substitute for node 1, we only have a naught left, so we have u1. At node 2 we have a naught plus 3x equals u2. At node 3 we have a naught plus 1.5x 1.5y equals u3. Or we could have just formulated the matrix as usual: 1 0 0 1 3 0 1 1.5 1.5 using the by just the coordinates. Can we do it the other way? So we know u1 equals, so a naught equals u1, since these are the variables unknowns. And okay, so I made a mistake here. Actually 3a1 1.5 a1 1.5 a2. So we have a1 equals u2 minus u1 by 3, a2 equals u2 minus u1 minus 1.5 a1 is, so 1.5 upon 3 would be 1 by 2, I believe. u3 minus u1 plus u1 by 2 would be minus u1 by 2, and again minus 2 by 2. So we substitute this back to first equation. So arranging the coefficient of u1 first, 1 minus x by 3 minus y by 2. linear coefficients of y, sorry, u2. We have sorry, so here we have x by 3 minus pi by 2, sorry, minus x by 3, oh, plus x by 3, sorry. Then we have another term, coefficient of root 3, that's only y. Till the end we have psi 1, this is our psi 1, this is the psi 2. Let's up there, save some space. Okay, so this is our psi 2. Now we need to find a centroid. So centroid is basically the average of each coordinate. So 0 plus 1.5 plus 3 by 3, comma 0 plus 0 plus 1.5 by 3. The centroid is 4.5 by 3 is 1.5, comma,
zero point 0.5.
yeah, thanks. This is the coordinates of the centroid. So we find psi 1 at centroid, we get it's 1.5 comma 1 minus 1.5 by 3 minus 0.5 by 2. So this again is zero point 0.5, zero point 0.5 minus 0.5 by 2. So that's plus basically. It's zero point 0.5. Yeah, it's 0.25, I guess.
Yes.
Psi 2 at C, 1.5 by 3 minus zero point 0.5 by 2,
Is also 0.25.
and psi 3 is just y, that's zero point 0.5. Okay,
Yeah.
so it's interesting that the psi 1 and psi 2 are giving exact value at centroid, but psi 3 is not doing that. Okay, and we can just verify that psi 1 at 0, 0 will give 1, of
Yeah.
course, and at 3 comma 0 it will give
0.
0, right? And at 1.5 comma 1.5,
No, I think this will not be 0.
so can we check the
Yeah.
coefficient?
Yeah. 1 minus x by 3 minus y by 2 u1 u2 x by 4 minus y by 2, okay, u2 3. Yeah, this UE is correct. UE above 7 centimeter and 1 by 3.
Oh, I forgot something here. 8,000 divided by 125.
Yeah, yeah, yeah. This,
Okay, we'll have to redo this now. So we will try to correct it here. Okay. So U3 by 1.5. Simplify this. This will be 2 by 2 U3 by 3. Minus 2 U1 by 3 and minus 2 by 3 minus plus U1 by 3. So this is 2 by 3 U3, and we'll merge the U1 term. We'll be left with minus 2 by 3 plus 1 by 3 will give us minus 1 by 3, right? Okay, so we have to modify our A2. So for coefficient of U1, we have 1000 divided by 3. For U2, we have x by 3 is equal, right? Then we have y by 3 again. And for U3, we have 2y by 3. So I hope we'll just verify this first. So psi1 at 1 is fine. Psi1 at 2 is also fine. Psi1 at 3 is also 1.5 by 3 minus 1.5 by 3 will give 3 by minus 3 by 3. It is 1 minus 1. This is also correct, right? Psi1 is satisfying for all three nodes. Psi2 for 1, 0, 0, it will be 0.
0,
At 3, 0, it will be 1,
1.
right? And for 1.5, 1.5,
Yeah,
it will be
0,
0. And side 3 at 1.5, 1.5 will give us 1, right?
1.
and 000 and 30 plus 0. This is right. We'll calculate psi 1 at C again. We have 1.5, 0.5, 1 minus 0.5 by 3 minus 0.5 by 3. So we have zero point 0.5. So we have 1 minus zero point 0.5 is zero point 0.5 minus zero point 0.5 by 3. We have 2 by 3, 1.5. But actually, we can just say 1 by 3, 0.33 basically. 0.5 by 3 minus 0.5 by 3. This is 1 by 3 again. 2 by 3 into 0.5. This again is going to be 1 by 3. Okay. Now this makes more sense. All three are equal at the centroid. That's why I was fishy last time. They were not equal.
Yeah.
Okay, so I hope this was clear.
Yeah.
Okay, so find the connectivity matrix for the following mesh. Also find the global strictness matrix. Okay, so we'll start connectivity matrix. So how many number of rows would be there?
For an element or globally you are asking?
For the connectivity matrix, how many rows? So connectivity matrix has the data for the connectivity of each element, which global nodes are present in each element, right?
Okay. Okay.
So the number of rows would be equal to the number of elements. So we'll have to specify the nodes for each element. And how many number of columns would be there? This is a little tricky here for this mesh.
Because there are a different number of nodes
Yeah,
at the
yeah.
corners. Yes.
Yes. So here we have a quadrilateral element. For that, it should be four
Four.
columns,
Yes.
but
Yes.
for triangular, it should be three.
Three. Yeah.
So we'll start the with the first row. So what would be the entries for the first row?
Uh, it will simply be 2 4 3 1. I guess.
2431. Why?
No,
So
no, no.
you see this figure, the numbers with red are the global numbers, and the
Yes.
numbers with black are the local node numbers inside.
Yeah. Yeah.
So for so this the each column represents the local node number, and the entry is the global node number corresponding to that local node number. So we'll see at one we have
One,
global node, right? So we'll start with one. For two we have two.
two,
For three we have four.
four. Yeah,
For four we have three.
three. Yeah.
So then for row two, what should be the entry?
For one, it should be four.
Right.
For two, it should be five.
Yes.
For three, it should be three.
Yes. And then nothing.
Yeah.
And for three, for third row we
For one, it should be four.
yes.
For two, it should be seven. And for three, it should be five.
Yes. Then we have for four we have
For one, four. For two, it is six. And for three, it is seven.
yes, right. Okay, that's correct. So this would be a connectivity matrix, right? So it's interesting with this thing. If we have even if we have different kind of elements, we can using this matrix we can solve a problem. Hopefully, I don't think there should be an issue with this.
No.
Okay. Then we have this mesh. What should be the connectivity matrix for this? Okay, we had some more parts. So we have to find the global stiffness matrix also
Yeah, yeah,
using
yeah.
this. For 4 elements at least we'll try. So how many total number of rows and columns should be there for the global stiffness matrix?
If we consider the single degree of freedom at each node, then it should be
Yes.
7 cross 7.
Yes, right. We have so we'll start with the we'll start with first row. So okay, so we'll do with for K11. So node 1 is part of only one element, right?
Yeah.
So it should have contribution from that element only. So K11 of 1, right? Uh, we'll do for 4, 4 and 3. First for 3, 3. So 3, 3, 3, node 3 is part of two elements here.
Yeah.
So it should have contribution from element 1 and 2.
Yeah.
And for element 1, it's the fourth node.
Yes.
So for element 1, it's 4, 4 plus for element 2, it's 3, 3.
3 3. Yeah.
And for 3, 4, 3, 4 is part of both element 1 and 2 again.
Yeah.
There's the connectivity between 3 and 4 for two elements. So for
Okay, 3
element, yeah. So what should be the entry? Tell me. For element 1, it should be
K 3 3, I guess. Let it display.
for I am talking about the entry 3, 4 of the global. What should be the contribution from element 1?
Actually, the figure is not
Okay.
totally. Can you just scroll up? Yeah.
You can actually look at this B matrix here, connectivity matrix. It will give you better idea. Okay, so we want the global entry for 3 4. So global node 3 4 and the contribution for it from element 1. So global node 3 3 4 and element 1 is present, right? But the for element 1 they are actually 4 3. So node global node 3 is actually local node 4
Mm-hmm.
and global node 4 is actually local node 3.
Yeah,
So 3 4 it should be 4 3 of k1, right? And for element 2,
it should be 4 1, I think. K412. Element 2.
for element 2,
The node.
for element 2 we are looking for this one 3 4, right? So for element 2 the node 3 is the global node 3 is local node 3,
Yeah,
but
yeah.
global node 4 is
Local node 1.
yeah, so it should be 3 1.
Okay.
I hope that's clear.
Yeah.
So likewise okay, for 4 4 it's interesting, we'll write that. So how many contribution would be there for 4 4?
Okay. I think there is nothing for 4 4 because each element.
So whenever we are looking at any contribution, uh, so suppose we are looking at 3 4, we already looked at 3 4. We had to see that 3 and 4 are connected in which of these elements. So we saw that 3 and 4 form a line which is part of element 1 and element 2 also, right? But
Yeah.
if we are to look at 3 3, so the node connecting itself is uh, so so we just need to see that 3 is part of which of the elements. 3 is present in element 1 also
Yes.
and
Into
element
also.
2 also. So K3 should have contribution from both.
Yeah.
And when we talk about a node 4, the contribution 4 4, so we just see that 4 node 4 is part of which of these elements.
Uh, it's the it's the part of oh 1 2 3 4.
Yeah,
All these are contributing. Yeah,
yes.
because this node in common.
Yeah, yeah. So this node is part of all 4 elements.
Okay.
So keep it at K4 4. So we have 1 from K1, K2 plus K3 plus K4. Now, what are the local numberings we have to check here? So for element 1,
K31 it is. No.
no, it's we are talking about 4 4, right?
Okay. Okay.
So whenever we are trying to find any K ij, we just transform that to the respective local number, local node number. And if it's just II position, like we have 4 4, we just transfer that. Both should be same, right? After transferring local numbers.
Okay.
So we just need to see that for element 1, what is the local numbering for the global node 4?
It is 3
So it should be 3 3, right?
3 3. Okay.
For K2,
It should be K11. Uh, Also K11 and for 4 also
Yeah.
K11.
So you just have, if you just look at this matrix here,
Okay.
you just identify where all four is coming,
Okay.
and with the from the corresponding position of that global node number in the
Mm-hmm.
matrix, we just use the corresponding value. So here four is at the third row, third number, third column.
Okay.
So we just know that for it we have to pick the 3 3 entry from element one,
Okay.
and here for all these you have to pick up the 1 1 entry for all the other elements. So yeah, so that's how we create the logic in a program also.
If we are talking about K16 in the global matrix here,
K 16.
16, yeah.
Yes.
So basically, these Kij means this I and J are representing the global nomenclature of nodes.
Yes. Yes. Right.
Okay, so basically, what this K16 showed, it is something. If you are transferring some results from node 1 to node 6, so what will be the contribution of this stiffness from node 1 to node 6, or what it is?
If we talk about that, it basically means that whatever the interior we are calculating,
Okay,
yeah, how is it shared between the two nodes? I think something like that. Can't actually pinpoint the actual physical term for that. So that is why these kind of this stiffness matrix will form that what do we call that, uh, spa- kind of sparse pattern.
okay, okay. Because in the abacus and ANSYS, in both, I have seen this sparse matrix
Yeah.
term a lot of times.
Yes. 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 That
Okay,
is why. So usually in normal 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 kind of it's a simple problem with the normal symmetry. It's not two-way symmetry.
okay,
uh, we will see that the entries of the diagonals, like we have 1 6 here. So what should be the entry for 1 6 here? Global entry 1 6.
16.
So you see 1 and 6 are not connected within any
Yes,
element. Okay.
yes,
So
yes,
that
yes.
means there is no contribution of 1 6.
Okay, okay,
So it's zero.
okay,
So more the far from the diagonal you go in this global matrix, you'll get more zero entries.
okay,
Majority of the non-zero entries would come around the this diagonal, the diagonal in the
okay,
matrix.
okay,
So
okay,
to avoid the extra storage space, to minimize our storage use, we there's something called this sparse matrix.
okay.
That's why you've seen in many some FEM solvers. So what
Hmm.
they do is they don't store, they just look at the mesh, and
Mm-hmm.
from the mesh they know which nodes are not connected, and they'll
Okay,
know that the corresponding global matrix values would, which of the corresponding global matrix value would be zero. Then they don't assign any variable for that. They reduce the matrix so such that only the entries near the diagonal would be stored. So only around these entries would be stored according to the
okay,
style of the data structure.
okay,
These entries are not even stored because the the solver would know from the given mesh which of the entries would be zero.
okay. So it should be some lower triangular matrix type.
It's not even a matrix. it's some random data structure. I am not sure about how it actually looks, but
Okay.
kind of just some entries bunched together, grouped together, which
Okay.
are which are corresponding to the entries near the diagonal.
Okay. Okay. And
So
can you scroll up for this figure? Yeah.
yes,
And if any person talk about the K46, suppose K46.
yes,
So as these nodes are connected by a single edge,
yes.
which is going from 4 to 6. So is there any definite value apart from 0 for this? What should be the value for K46 here?
So the value for K46 would depend on what kind of element is connecting them.
Okay.
Depending on the element, we'll have our approximation function,
Okay.
and on the basis of those approximation function, we'll get the whatever the value should be there.
So means to fill up this entry K46, we have to know the path from 4 to 6, how, what type of pattern it is
Yeah.
obeying. Okay, okay, okay,
What kind of element is it a part of?
okay. So, but from here, can we now write this value K46?
Yes, yes.
Okay,
We just need to know the mesh data basically. If we know
okay,
the mesh data and we have a choice for approximation function, we can
mm-hmm.
do that.
Okay,
Those two are the requirements.
okay. No, no, no. Actually, I'm talking about here. If I want to write this K46, so in terms of local nodes, how it should be written, I'm asking about.
Okay, in terms of local nodes, right?
Yeah, yeah, yeah.
Okay, yeah. So we see that we just look at K46 part of which element. So right
It
now,
is four,
4 and 6 are together present only in,
four.
yeah, this element, right?
Okay.
So for the fourth element, it is actually the entry 1 2.
Yeah.
So we just write this as, so 4 and 6 is K1 2 of 4.
Okay. Okay. Okay.
Okay.
Yeah. Now I understood this.
Yeah. Yeah. So if we have larger meshes, you'll see that the so we when we are assigning the number to the node, we usually follow some path, right? We start number 1 2 3 4 5 6 like that.
Okay.
So that's why the nodes which are far away uh, would correspond to an off diagonal element usually, the element which are far from the diagonal in the global matrix. So
Okay.
that's why
Okay.
they'll have no connectivity, and that's why those entry would be zero.
Okay.
Like this here is a short matrix, so we see that 4 and 6 have connected. So 4 and 6 actually not too far, but we see that 1 1 5 1 7 1 6 two
Okay.
5 2 7 2 6 all would be
Mhm.
zero,
Yeah.
right? So
Okay.
most of these entries would be zero.
So as I can understand from here, using this sparse metric technique,
Yes,
we can even reduce some computational cost also.
yes, yes. That is the purpose for this.
Okay. Okay. Okay.
So yeah, mainly storage space is reduced by a lot. That means like
Okay.
it's really makes a big difference.
Okay.
So I use a library which is called deal2. So
Okay.
there we have function directly for that. So
Okay.
when we create a matrix,
Mm-hmm.
we have a library called sparse direct, which creates a sparse matrix on its own in the
Okay.
background, and we just need to enter the data to it. It will automatically manipulate.
Okay.
Okay, so now we have this mesh. So I hope we can write the connectivity matrix without any problem here.
Okay.
First of all, total number of rows would be,
Total number of 1, 2, 3, 4, 5, 6.
yeah, according to each element.
Yeah.
Then we have total number of columns as,
This time these should be 3.
yes. So we have only triangular elements now.
Yeah.
So can we just quickly write the each entry for each row?
Yeah. Yeah. For one
So
it
we have,
should be. Yeah. It's
right?
2. Yeah.
I'll just quickly
It's
write
4.
it, just verify.
Yeah.
So for element 2 we have 1, 4,
Yeah. 3. Yeah.
for element
3, 4, 5.
3, 3, 4, 5. No, it's not 3, 4, 5.
No,
It's
no.
4,
4,
5, 3.
5, 3 it is. 4, 5, 3 it is. Yeah. Next is 4, 6, 5.
Yes, 4, 6, 5.
Yeah. And then for element 5 it is 6, 7, 5.
Yes.
And
Then,
for element 6 it is 2, 6, 4.
right. Very good. So you see, I'll tell you one more thing here that
Yeah.
usually you see the trend of numbering the local nodes.
Okay.
So it's up to us, right, to whatever local node number we can give to each element, right?
Okay.
But we usually see the trend of these local node numbers going anti-clockwise.
Yeah.
We mostly rarely see following this here also, yeah. So in each element it's anti-clockwise. So I think this is the from what I remember is to maintain consistency of the Jacobian. If we'll change this direction of numbering, the determinant of the Jacobian will change its sign.
Okay.
I can't remember it exactly, but what from what I remember, this is actually the case. So
Okay.
it caused some inconsistency in calculations. So
Yeah. Actually, let me tell you one thing.
yeah, yeah.
What I was experiencing. One day I have designed a particular bolt with hex elements,
Hmm.
and what was observed when there was a transition from the bolt pretension surface to the bottom of that bolt body, there was a negative value of Jacobian I have observed. But when I have renumbered those nodes using the renumbering tool, it was not so. So I think what are you saying that is applicable regarding the node numbering and Jacobian?
Yes, 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 yes. I think so. This
Yeah.
is good example actually.
Yeah, because
So
my senior was asking me again and again how it is possible that this much of finer mesh has the negative Jacobian value. So then,
yeah, yeah, yeah. So you change from hex element to which elements?
no, I have not changed from hex element to the element. Hex elements were remain as it is. Simply, I have renumbered all the nodes that bolt was containing. Yeah, yeah,
Okay, okay, okay.
yeah,
That's nice.
yeah,
So yes, that's why we try to maintain consistency in numbering. So
yeah,
usually we'll see we follow this anti-clockwise pattern.
yeah,
Okay, so do we need to do the exercise for global stiffness matrix? Can we do this?
yeah, yeah, yeah.
This time we'll not look at the figure. We'll just look at this P matrix.
Okay, okay.
This would be more helpful doing.
Yeah,
So once again, total number of the size of the matrix.
will be 6 by 6.
Yes. So we'll do one or two entries.
Mm.
Okay, so we'll start with 2 4.
2 4. 2 4. Okay. 2 to 4 is present in only element number 1 and element number 6 also.
Oh, sorry, it should be 6 by 6, right? We have
Yeah, yeah,
6.
yeah, yeah.
Sorry, 7 by 7. Sorry, 7.
The nodes are 7
Yes,
global. Okay. Oh, yeah, yeah.
7 by 7. So, yeah, 2 4. What did you say earlier? I didn't understand.
2 4 is present in element 1 and
Yes,
element 6 also.
yes. 2 4 is present in element 6 also, that's right.
Yeah,
So, one from element 1, one from element 6.
yeah.
That should be the local node number.
Uh, can you just scroll up someone? Yeah, yeah, yeah. K231.
Yes, right. Yes, that's right. And for 6,
K13.
yeah, correct.
Okay.
Okay, so can we do 5 7? K 5 7?
5 7. There is nothing. There is nothing present as 5 7 in any element. No, no. I think it is present in element number 5.
Yeah, yeah.
So it should be K325.
3
32.
yeah. And we have 4 7.
4 7. This time, I think there is nothing.
So that is 0.
Yeah,
So I hope the concept is clear from this, right?
yeah, yeah,
Okay, then we can move further. There's
yeah.
no doubt here. Yeah, one more thing that I remembered from this, that for these meshes, can we say what is the total number of element level equation and total number of global equations?
The
We have
number of
started the
elements.
first mesh.
Okay. Total number of elements. So total number of element level equations. I think how many um, degrees of freedom for all these elements. Yeah, there should be that much number of equations for the elemental equations, and for globally what should be the size. But yeah, after applying the Dirichlet boundary condition, what we can say, I think the number of nodes those are present in our mesh, the number of elemental equations should be the equal to that much amount of number of nodes.
You mean the global total number of global equations?
Actually, I'm not getting what is the meaning of this number of elemental equation. Means it is asking about.
It is
Yeah.
asking that total number of equations combined for each element. So when we uh,
Okay.
make the when we calculate the element level stiffness matrix,
Okay. Okay. Okay.
so that is actually whatever size of the stiffness matrix is, that is total number of equations corresponding to that element that we are going to solve.
Yeah. So I think that should be the number of nodes corresponding to that particular element.
Yes. So and so we have four elements here. So for first
Yeah.
element we have four nodes, so we have four equations.
Yeah.
For second we have three, third we have three, for fourth we have three.
Yeah.
So we have 13 equations in total for element. But
Yeah.
when we do the assembly,
Yeah.
these equations are reduced here.
Yeah.
So then the equation merge. Finally, the total number of global equations are equal to the total number of global nodes.
Yes.
So,
Okay.
and for this mesh,
This mesh elemental equations are 6 into 3, 18.
yes, and number of global equations would be
Number of global equations would be 7.
yes, that's right. Okay, so for this it was 14 and 7.
7, 7. Yeah.
This was 18 and 7.
Yeah.
So you see the above two mesh look uh, that they're kind of same, right? Not same, but they have same number of nodes.
Yeah.
And at the end, we are solving the same number of equations. But the
Yeah.
way we have discretized the domain, or we have
Yeah.
made the generated the mesh,
Hmm.
uh, will that will affect the total number of element level equations.
Yes.
So
Yes.
So, in the last class also we discussed the difference between the quadrilateral and triangular areas. So, if we are meshing the same domain with a quadrilateral mesh,
Hmm.
then we'll have lesser number of
Yeah.
element level equations. So
Yes.
that saves us a lot of computation.
Yeah. Yeah. Yeah.
So
That's why in general. That's why in general, when we have the more complex BIW parts,
mhm,
so if we go for tet mesh there, as you can, as you know, in general, what industries are using for tet mesh, this second order of element they are using.
yes,
But when they want to reduce the computational cost, they hire the engineers who are able to do the shell meshing for that also.
oh,
Yeah. Yeah, I am also such kind of person who generally deals these BIW parts to treat as the shell shell mesh. Yeah.
that's interesting.
Yeah.
So last time also we discussed this discussion always when we study FEM, that which
Yeah.
mesh to use, which is better, triangular or quadrilateral.
Yeah. Actually, Umer, one more thing I wanted to ask you. In general, people say that when we discretize some domain by only the use of the tet elements without using the hex elements, the stiffness will be more. So basically, if we consider two elements, one is hex and one is tet, and the area is same, means cross sectional area is same, and we are using these two elements in case of bending. So, is there any definite relationship of the greater or smaller between these two elements in terms of stiffness? Means for tet elements, the stiffness should always be high. For hex elements, the stiffness should always be lesser. So these type of questions in general, industry persons are asking more and more.
Oh, I'll have to look into this.
Yeah, actually, I thought this in the section using the concept of section modulus also.
Mhm.
For example, yeah, if the cross-sectional area of these two elements are same, but I didn't get the actual way to interpret the comparison between these two.
Okay, okay.
Yeah,
So I'll look into this. So
yeah,
you want to know some this comparison between the stiffness matrix
yeah.
between
Hmm.
the tet element and the hex elements.
Yes, yes, yes.
Okay, I'll see if I'll find anything for this.
Okay.
Okay, so
Yeah.
we can move on to the next question. So consider this quadrilateral element shown in figure 1. Find the mapping function. Also calculate the Jacobian. So to how do we map an element? What is the formula for mapping function? Actually,
Yeah, this is equal to, yeah, mi at xi.
and same for y.
Yeah.
So what are the standard shape functions for a quadrilateral element?
1/4 zeta by 4.
Yeah.
So this is by idealizing this quadrilateral elements as the coincidence and parallel to the principal axis or master plane axis. Means xi axis and eta axis if we consider one quadrilateral element
Uh-huh.
parallel to these axes.
Uh-huh.
So those four shape functions that you have written in this slide.
Yes. So these
So
are
this,
for the master element, right?
yeah, yeah, yeah.
So for the element that ranges from -1 to +1 in xi and eta coordinates.
Okay, okay, got it. Yeah,
Just for this tandem.
okay.
Okay, so now we just have to put them in the formula.
Yeah.
So the coefficient of n1 is anyway 0. So start
Mhm.
with n2, 5 n2 plus, how come this is 5 minus 1? It's 4 pi. Okay, anyway, I took this figure from the last year's FEM course.
Okay.
4 n3 plus, this is 1 n4. So we have 5 by 4 n raised, we have n4 as, so how can we simplify this easily? Here 1 plus y, 1 by 4, 1 minus y. So that makes 1 plus 1 by 4, 5 by 4, and y minus 1 by xi by 4 is, so plus 3 xi by 4. Can we simplify this further?
Yeah. No, no. Actually, I have to. We have to expand this further. Then only it is possible.
Okay.
That's right. Yeah.
5 plus 0, 5 beta plus 3 is beta. So we have 5 by 10 plus 5 plus 3, 8
Yeah.
inside,
Wait. Yeah.
minus 5 beta plus 5 beta is 0, and we have minus 5 plus 3 is minus 2.
Minus two. Yeah.
So, so this is our x.
Yeah.
And for y, we have minus 1 and 2, and
Yeah.
5 and
Five.
3,
Yeah. 5 and 3 plus 4.
but out of space, I didn't do it properly. Plus 5 and 3
Yeah.
plus 4 and 4. Go ahead, explain this. Yes. So 8 by 4 plus beta 1. So what is our answer? We have 5 by 4 plus 1,
9 by 4 it
9 by
is.
4
Yeah.
plus
Xi by 4.
xi by 4.
Yeah.
So now we expand. So 9 by 4, minus 1 plus 9, 8, minus xi plus xi 0, plus alpha plus beta is delta, and we have plus alpha xi plus beta xi is 2 xi. Okay, I hope this is correct.
Yeah.
All right, so to find the elements of Jacobian, just take the derivative here. So we have 8 by 4 and minus 2 beta, and 8
Yeah.
by 4 minus 2 beta which have minus.
Yeah.
Okay, then for here we have two eta y equal to 10 by 4 plus y.
Yeah.
So if you want to find a Jacobian,
Yes.
determinant of Jacobian actually,
Yes.
so I have my elements right multiplied together. So we have 2 minus y by 2 times 5 plus sorry minus 0.4 times 5. So we have 2 multiplied by 2 5 plus 2 multiplied by 2 7 plus 5 delta by 4 plus delta by 4. Plus 7 so minus 11. It's a linear function now.
Yeah.
Okay, so now we have a rather simpler quadratic element finding the mapping a one dimensional plane. So we have n1 0 into n1
Yeah.
plus n2 plus 10 into 2 plus 0 into 4 inside n2 n3. Then 1 plus 4
Yes. 1 plus I 1 minus eta 1 by 4 7 plus eta
1 minus eta plus 1 plus eta we have 2
2. Yeah.
here
Yeah.
and y we have n3 plus n4 plus plus n4 times
2.
1 by 2 again again
1 plus I by 2.
plus etc. Then if we find the elements of Jacobian, we have let me see. So determinant of Jacobian would be larger than lambda.
Yeah.
If you see
it's a constant function. For example,
Yeah.
linear function we have taken.
Yeah.
So this kind of mapping, it's just actually a stretching operation.
Yeah.
So it's just a transformation with a stretch. So the Jacobian for this kind of transformation is a constant. Okay, so this is it. Okay, now we can do some cross integration problem. So we have this 6y dx dy from 0 to 1, 0 to 1. So what we do is we should know the mapping. So basically what we have now is this domain,
Yeah.
and we just need to know the mapping function, right? And in last problem, this is exactly what we did. It was the same coordinate belt. So we can just use these mappings and Jacobian, right?
Yeah.
Is equal to 1 plus pi by 2 is double prime, and our Jacobian is double prime. So we can quickly transform this integral from 0 to 1 x by dx dy to minus 1 to 1 x minus 1. X is 1 plus 1 plus minus 40 multiplied by x.
I hope it's a determinant of Jacobian, not any inverse of it, right?
Yeah. It is determinant. Yeah.
So we have 1 by 4 times our integral is 1 by 8.
So we'll try with 1 point.
Okay, 1 by 8 into
So our 1 point is 0, 0, and our weight function is 4. So we'll just simulate it. 1 plus 0, 0, and multiplied by 4. So our answer is 4 by 4. If we use, that means 4 constant. We have 1 by 8 plus 1 by root 3,
Yeah.
1 by root 3
Weight function is 1.
plus 1 by root 3 and minus 1 by root 3 and minus 1 by root 3 is cancelled. 1 by root 3 1 plus 1 by root 3 and minus 1 by root 3
Okay.
Okay, so let's do one calculator for this.
Yeah.
Or we can try to simplify it.
This will be 1 minus a minus 0 square 1 plus 1 by root 3 minus 2 by root 3 minus plus ba minus b. So combine these two terms.
Yeah. 1 minus 1 by 3 is 2 by 3.
1 minus 1 by 3. 2
Yeah.
times 1 by 3. Then we
Yeah.
have a plus b whole square, that is 1 plus
Plus 1 by 3 plus 2 by root 3. Yeah. This
so
is
cancel.
cancelled. Yeah.
So we have 2 times 1, 2 times 1 by 3, 2 plus 2 by 3, then again 2 minus, so this term is 2 times 1 by 3 here, and
Mm-hmm.
this is also 2 times, so this is also 2 times. If we divide these two, we get 2 times 1 by 3,
Cancelled.
so
Yeah.
that will also cancel. So at the end we are left with 2 by
4.
2. 4.
4. Yeah.
4 by 8 is 2.
No, 4 by 8 is 1 by 2.
Sorry, sorry. My bad. 4 by 8 is 1 by 2. So we get exactly the same answer, right?
Yeah.
That means only 1 point was sufficient for this integral.
Yes.
Okay.
How did you recognize this integral of xy dx dy from 0 to 1, 0 to 1? It is just identical to the Jacobian that we have defined for the last problem.
Okay. So if you look at the limits,
Okay.
so x is basically this limit actually means that x independently varies from 0 to 1 plus 1,
Yeah. Yeah.
and y varies from
Okay.
0 to plus 1. So this
Okay.
is actually the case of the two field. It's it's an area integral over
Mm-hmm.
a square of size 1 from 0 to 1.
Yes. Yes. Okay.
Okay, so now we have again the same integral, same limits actually, with the integrand change to sine x pi.
Yeah.
So we'll try to do this also. So again x is 1 plus y 1 plus eta by 2. Jacobian is 1 by 4. So our integral 0 to 1 sine xy dx dy changes to so we'll use 1, so that is 0. We have 1 by 4 sine 1 plus 0 1 plus 0 by 4 into 4. That's the weight. So we have sine of 1 by 4. We'll leave it like this for now
Yeah.
until we have to compare it. Then for r equals to 2, we have 1 by 4 into sine of 1 minus 3. Okay, so we just have to apply sine on the last thing that we did.
Yeah.
So we'll simplify this. Not easier as last time. The sine function.
Yes.
So I'll just use my calculator now finally. So loading. Okay. Yes. change sign. This is my course. So this is the 3 lines. So
Yeah.
then sine of 1 by 4 is what will be the count? 2, 4, 7. Okay, so the two results are approximately close.
Yes.
So that means the results make sense. So since it's a sine function, sorry, okay, let's start. So it's a sine function, then there would be some error, and using the Gauss quadrature rule, we can never always get the same result.
Yes.
The exact result, because it's designed for polynomials.
Yeah.
Okay, so I think we are out of time now.
Yes.
We can conclude the session here, and we'll meet again this coming Tuesday. There, I'll try to discuss uh, that example, that assignment question again in the 2D code.
Yeah.
Okay, so if there's any doubt, we can discuss now. Otherwise, we can conclude the session.
One thing I want to ask about the final exam. There means, for example, in a particular assignment, we are getting a large size problem where we have to start from end. We have to start from stiffness matrix to do the unknown calculations. So starting from that to the end, we will get these type of questions, or there could be some smaller size problems that you are taking in these doubt sessions also.
So I personally don't have much experience with the assignment with these exam questions, but I can tell you that the that those would be doable in that time. Not sure if
Okay.
they'll follow the pattern of my doubt, these questions that I'm discussing here,
Mm-hmm.
because that is something separate.
Okay.
But hopefully it should be reasonable. It should be done within the reasonable amount of time. It won't be that too long question that we see in the assignments.
Okay.
And you can ask in the this discussion forum also. I think
Okay.
the people who set this exam question, they can answer you better.
Okay. And regarding this MATLAB application, so is it compulsory to use the MATLAB to solve the questions in the final exam, or manually also we can do the same?
Uh, I think this exam is held at some center, right? NPTEL center, or is it a
Yes.
take home exam?
No, 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 no. There is yeah. This is centers are there.
Uh, so I don't think you will have a system there, would you? With the MATLAB installed on it.
Yeah, actually, because that's why I am asking, because if a particular center is there,
Yeah, yeah,
so
I
yeah,
know.
I also don't think that MATLAB should be installed in the particular system
Yes,
on
yes,
which I will give the exam. Yeah.
yeah. So
So
that this also a question also you can take up in the discussion forum.
Okay.
The people who are to set these questions in this exam pattern, they can answer you better because
Okay.
we as TS don't have much information about that those things.
Okay. And one last thing that can you suggest some standard textbook regarding the advanced solid mechanics from where I can do some study about the advanced things related to the theories of failure or all these things? Means actually here what I have seen on the Google, and there are so many books referred by the students and professors, and but from your point of view, is there any thing that is useful for FEM and solid mechanics for both?
Okay. For solid mechanics, I used to follow a book called Maze. I forgot the first name of the author. It's
Okay.
something called Continuum Mechanics by Maze,
Okay.
MASE.
MASE.
Yeah,
Okay.
and for FA, but that I don't think that book covers theories of failure. It's basic, like it's a basics of the advanced mechanics solid.
Okay.
And for FEM there are a couple of books like there's Jacob Fish
Yeah.
and there's what is it called, Ted Belichko.
Okay.
I did those a little, not completely, but and for the one pretty famous standard book is Jeevan Reddy.
Yeah. Jane Reddy is there.
That
Yeah.
is a quite famous book there.
Yeah.
So I have not completely followed any book thoroughly, but I have had you referred some books at some point of time.
Okay. What is your point of view about LS Srinath, Advanced Solid Mechanics by LS Srinath? Because that person belongs to your college.
Oh yeah,
Yeah.
I haven't read that. Honestly, I haven't read that, so I can't give any opinion on that.
Okay. Okay.
So yeah, I have only gone through Maze because the professor there under whom I was taking that course, he was following that.
Okay. Okay. Actually, what I have faced, I think around 2 years I have spent in the industry. From 2021, I have started my job. So basically, if we have the international client like Mercedes-Benz or all these type of international brands, they used to give the materials which are orthotropic and anisotropic also, and to justify the results in terms of the mechanical properties of the orthotropic material and anisotropic material,
Hmm.
we need some thorough knowledge about what is the exact relationship between the elastic coefficients,
Hmm.
what is the exact relationship between all the other parameters also in terms of mechanical properties.
Yeah.
So that's why I'm asking this, if there any textbook which covers all these things in its yeah.
I'll take a look. But with respect to FEM, these two books, Jacob Fish and Ted Belichko, are really nice book.
Okay.
And I don't know if these things are much discussed in Mace.
Okay. Okay. Yeah. Okay. Got it.
Okay, so meanwhile I'll take a look at those books again. I'll see if I'll find anything new. I'll let you know.
Yeah. Yeah. If you will find any, you know what I am asking about those things in
Yeah,
any advanced solid mechanics book. So please tell me.
sure, sure, sure. Of course. In fact, in Mace we studied about this reduction of this elastic constant, the
Okay.
this fourth order tensor, elasticity tensor, how
Okay.
different symmetries are applied and uh, the number of elastic constant reduced from 81 to finally, I think, from for orthotropic and finally for isotropic case.
Yeah. Yeah. Yeah.
So we did study that in the book.
Mm, okay. Got
Okay,
it.
so
Okay. Thank you.
okay, thank you so much for joining. I'll see
Okay.
you again next time.
Okay.
Okay, bye.
Bye. Bye.